Linear versus exponential. In this video, you'll learn how to compare growth patterns using calculations and graphs. Linear and exponential functions can both represent a constant growth or decay. Linear functions show patterns of addition and subtraction, while exponential functions show patterns of multiplication and division. So let's dive into linear functions first. The growth in a linear function adds the same amount each step, and the graph of a linear function is a straight line. The formula that we use for linear functions is y equals mx plus b, where m represents our slope and b represents our y-intercept. An example of a linear function might be that a bank account has $20 in it and it adds $5 every week. Now let's look at exponential functions. The growth in an exponential function will multiply by the same factor each step. The graph will show a curve that starts out slow and then rapidly increases. The formula for an exponential function is y equals a times b to the x power, where a represents our initial amount and b represents our growth. An example might be that we start with $3 and we double it every week. So now let's look at some examples. A magic genie grants you a choice between two bags. Bag A contains $1,000 and will increase by $200 a day. Bag B contains 1 penny and will double every day. The bag only grows if you leave it closed. Opening it will stop the pattern. Let's look at each bag and see how much we can earn. We'll start with bag A, and it says that it contains $1,000 and will increase by $200 a day. So we know we start with $1,000, and then we'll add 200x to represent the $200 that we get every day. Bag B contains a penny, and it will double every day. So we'll start with the 1 cent that we have, and then we'll multiply it by a factor of 2 since it's doubling. The exponent of x tells us the number of days that we'll leave it closed. Now that we know how much bag A and B will give us, let's use this table to figure out how much would give us more money after a certain amount of days. If we didn't let any days pass, then bag A would have the $1,000 that we started with, and bag B would have the penny that we started with. Now let's look how much we would have after 1 day. So in bag A, we'll replace x with 1, giving us 200 when we multiply, and adding that to the 1,000 that we have gives us a total of $1,200 after 1 day. Now let's look at bag B. So we'll replace x with 1 in this case as well, and 2 to the first power is still just 2. And when we multiply that by our penny, then we'll just have 2 cents. Now let's look at how much we'll have after 2 days. So in bag A, we'll replace x with 2. This gives us 400 when we multiply, and adding that to our original $1,000 gives us a total of 1,400 after 2 days. Now let's look at bag B. So x will be replaced with 2, and 2 to the second power gives us 4, and multiplying that by our penny gives us 4 cents. Now let's go to 7 days, so this will be a week after it passed. We'll replace x with 7, multiplying that gives us 1,400, and then adding it to the 1,000 gives us a value of 2,400 after a week. Now let's look at bag B. So replace x with 7, and 2 to the 7th power gives us 128. So when we multiply that by our penny, we'll be left with $1.28. So far we can see that bag A has a lot more money in it. Let's look at 2 weeks by looking at 14 days. So we'll replace x with 14, and multiplying that by 200 gives us an answer of 2,800. And when we add that to the 1,000, we get 3,800. Now let's look at bag B. So x will become 14, and 2 to the 14th power gives us a value of 16,384. Now we'll multiply by the penny, which gives us an answer of $163.84. So bag A is still a lot bigger, but bag B looks like it's growing pretty quickly. So let's look at 3 weeks by looking at 21 days. So x will become 21, and multiplying that by 200 will give us an answer of 4,200. So when we add the 1,000, we end up with 5,200 after 3 weeks. Now let's look at bag B. So x becomes 21, and 2 to the 21st power is 2,097,152. So that's a big number. When we multiply it by the penny, we get 20,971. So it's a lot less than the million that we just had, but it's more than bag A. So it looks like the longer that we let this bag grow, bag B will have a lot more money. It's growing at a lot faster of a rate. Here's another example. Your friends find another magical genie with 2 new bags. The genie doesn't tell you what is in the bag, he just gives you this following graph. So let's look at this graph. The x-axis represents the number of days that the bags are closed, and the y-axis tells us how much money it's worth. The green triangles represent purse A, and the red squares represent purse B. So between the days of 0 and 9, purse A has bigger values in it. On day 10, both of the purses have the same value. After 10 days, purse B has more money in it than purse A. This is because it's growing at a quicker rate. So the amount of money we have depends on how many days we want to wait. Linear functions will have more in the beginning, but they will grow a lot slower over time. On this example, we're going to decide which expression equals 2 to the 7th power. An exponent always tells us how much to multiply the base by, so this lets us know that B would be our answer, since that's the only one that multiplies over and over again. Our next example is to evaluate the expression 3 times 5 to the x power when x is 2. So we'll take the expression they gave us and replace x with 2. 5 squared gives us an answer of 25, and multiplying that by the 3 that we have gives us a final answer of 75. Our last example gives us a graph that shows the yearly balance in dollars of an investment account. What is the initial balance in the account? We can find the initial balance by looking at our y-intercept when x is 0. So we can see that we started with $1,000. Is the account growing by the same number each year? Well, if we look at how much it's growing in the first 4 years, we can see that it's going up by 2 to 300. But when we look farther on the graph between 10 and 14 years, the jump's a lot bigger. So those are going between like 5 to 600. So it's growing at a constant rate, but not by the same number. Now we're going to sketch a graph for an investment that starts with $2,000 and grows by $150 each year. So we'll put our first dot on 2,000 since that represents how much we started with. After each year, we'll add 150 to our amount. So we'll raise our dots by 150 on each step until we see a line forming. Now we have a graph for this investment. Let's recap what we've learned. Linear functions show a constant rate of increase or decrease with addition or subtraction. And exponential functions show a constant rate of increase or decrease with multiplication or division. Exponential functions grow slowly at first and then grow extremely fast the longer the function continues.